Okay, today we're going to do the second week of organic chemistry, and I think after the first week this little cartoon may actually make a little bit more sense. Although we're not having organic chemistry exam, we're going to just have two organic chemistry quizzes. After the organic chemistry quiz, hopefully you won't be dying. We're going to start talking about something called a substituted halogen or a substituted hydrocarbon. And the first of these that we're going to talk about are alcohols and esters. And first, it's important to know how these sorts of compounds are formed. And here's one option or one example of how an alcohol is formed. What you see here is the reaction where glucose is broken apart in two pieces to form two molecules of ethanol, which is an alcohol, and two molecules of carbon dioxide. And this process is actually what causes bread to rise, and the gas in the carbon dioxide is what causes the bread to rise. And also, this process can also be used in the fermentation of glucose to form things like beer, where you have alcohol plus carbonation. So an alcohol is a derivative of a hydrocarbon where a hydroxy group is substituted in place of a hydrogen atom. And you can see that over here on the right side of the equation. This ethanol is basically ethane with an OH on the end. Well, the alcohol has an OH. It does not, and I want to repeat this, it does not behave like a base that we've been talking about in the past. The above reaction, as I said, is used to produce most of what we call potable, which means drinkable or consumable ethanol. Ethanol is also a product when you add water in the presence of an acid to the alkene ethene. So if you add water to ethene in the presence of acid medium, you form the pictured ethanol on the right. And you can have more than one OH, and you can see here that the name tends to carry this OH. What you again have is the base name, which is based on the number of carbons that are present. And then with alcohols, you add an OH on the end. And if you have more than one OH, you have, like in this case, you have diol. On the right, you have triol. And the numbers tell you that both OHs are not on the same carbon, but on different carbons. So 1,2-ethadiol is a alcohol that has two carbons and two OHs, and each OH is on its own carbon. 1,2,3-propadiol is a three-carbon compound that has three OHs, each of which are on separate carbons. Now, if you had, for example, in the first one, if you had one, or let's take the one on the right, if you had, say, two OHs on the middle carbon and one on the end, then you'd have 1,2,2-propatriol. So alcohols, as I said, can contain more than one OH group, and this is just two common examples pictured here above. So let's take a look at this, and why don't you see, again, you can turn off the tape and write down the name if you want to, or think in your mind how you would name this, and then we'll move forward and name it. So the IUPAC name for this alkane, and then you would substitute the OH on the end for A and E. You have 1, 2, 3, 4, 5 carbons, so it's propane, but now it has the OH, so it's propanol, not propane, I'm sorry, pentane, so it's pentanol, and the OH is on the second carbon, so it's 2-pentanol. So the name of the alcohol pictured above is 2-pentanol. It can also be written as pentateuol. I think 2-pentanol is a little bit more is less cumbersome. So why don't you give the IUPAC name for this compound, stop the tape again, and write down on a piece of paper what the name is you think of this compound has. First of all, you would count the carbons without lifting your pencil. So you start here, 1, 2, 3, 4, 5, or 1, 2, 3, 4, 5. So it's pentane, but it's got an OH here on the second carbon, so it's pentanol. It also has a methyl on the second carbon, so it's 2-methyl, 2-pentanol. Now an ether looks like this. What you see here is two small chains, like a methyl, in this case a methyl and an ethyl, and they're linked together by an oxygen. So an ether is a compound that contains the functional group of an O in the middle of the chain, somewhere in the middle of the chain. Now if the O's on the end, it's a different compound, so the O has to be in the middle of the chain. The IUPAC naming system does not use or have prefixes for ethers. The long chain is the base chain, so the above would be methoxyethane. So the base chain is the longer of the two, which is a 2-carbon in this case. So the shorter chain is the prefix, so it's methoxy, oxy, as you go from left to right, in this case, methoxyethane. Another common name that would be used is shown at the bottom, and as a matter of fact, when I was in high school, this is the name we used, methyl ethyl ether. So if we saw the O, we knew we'd just write ether down. I will count either methyl ethyl ether or methoxyethane as correct, but methoxyethane is the IUPAC name for this drug, for this compound, excuse me. So what is the IUPAC name for this compound? Again, if you stop the tape and write it down, in this case, what you have are 2 ethanes. So there's no dominant chain, so it's ethane, so it's ethoxyethane or diethyl ether. So ethoxyethane or ethyl ethyl ether, but you usually just say diethyl ether. And what is the IUPAC name for this compound? Now the interesting part about this is the dominant chain, it's linked in the middle carbon. So you have an iso situation here. So you would call this 2-methoxypropane, the 2 telling you that the oxygen is connected to the 2, but then the common name is isopropyl methyl ether. Either name would be acceptable. The 2 tells you that the oxygen is attached to the second carbon on the propane. So 2-methoxypropane. Ethers are frequently produced by combining 2 alcohols in the presence of sulfuric acid. So here you have, and sulfuric acid tends to be a dehydrating agent, meaning that it removes water from a situation. So you have, in this case, 2 ethanols, and then at the end you have diethyl ether or ethoxyethane. Now the third functional group, so far to review briefly, we've talked about alcohols with the OH group, and the name has an OL on the end. And we've talked about the ethers, which is the oxygen in the middle of the chain. Now we're going to talk about ketones and aldehydes. And this functional group here shows an oxygen in the middle or on the end. If this double bond O is on the end, then it's an aldehyde. If the double bond O is anywhere other than the end, it is a ketone. So this is called a carbonyl group. When you have a carbon with a double bond oxygen coming off of it, it's called a carbonyl group. If the carbonyl group is on the end of the chain, then it's an aldehyde, like formaldehyde. If, on the other hand, the carbonyl group is anywhere other than the end, it's called a ketone, like acetone is an example of a ketone. So if on the left you see the functional group is on the end, the R representing the other part of the compound. If the functional group is anywhere but the end, which is shown by showing an R on either side on the right here, then it's a ketone. The naming is similar to the alkanes and alcohols, except with alcohol, remember it was OH on the OL on the end. Aldehyde, it's AL on the end. With ketone, it's ONE on the end. So you just have to remember that each of these have their own suffix. So for example, this compound on the left comes from ethane. It's an aldehyde because the O is on the end, and it is thus called ethanal, AL. This is also called acetaldehyde in the stores. On the right, you see the carbonyl group in the middle. It's a 4-carbon chain, so it's butane, but you put ONE on the end because it's ketone. One way to remember what the suffix is it's ketone, ONE, so it has an ONE on the end. It's an aldehyde, so it has al on the end. So that's one way to remember the suffix that's used for each of these. When you write it in text, the aldehyde is usually written CHO, whereas the ketone is written as just CO. Now the carbonyl group is polar, and the geometry of the carbonyl group causes the geometry of the bonds around the central atom are trigonal planar. So you have an sp2 type situation with a carbonyl group. Alcohols are oxidized to form the carbonyl group. If the OH is somewhere in the middle of the chain, then you form a ketone. If the OH is on the end, then you form an aldehyde. So you have molecule A, B, and C. So for molecules which are on the right here, for molecules A, B, and C above, does each represent an oxidation or a reduction of ethanol as shown on the left? So in each of these cases, does A, B, or C represents oxidation or a reduction? Stop the tape and think about that and see what you think. A represents a reduction because an oxygen is replaced by a hydrogen. So A is a reduction, and you're going from ethanol to ethane. B represents an oxidation, a single oxidation, and you go from ethanol to ethanal. And C represents a double oxidation, and therefore you go from ethanol to ethanal to ethanoic acid. We haven't talked about the ethanoic acid yet. But in the second case, in B, a bond of hydrogen is replaced by a bond to oxygen. In C, 2 bonds of hydrogen are replaced by oxygen. Therefore, in the first you have a single oxidation. In the second, you have double oxidation. Aldehydes are produced by the oxidation of an alcohol. Shown here is propanol oxidized to form propanal. However, if the OH group is not on the end of the alcohol, instead it's in the middle, then the oxidation results in a ketone as opposed to an aldehyde. So you go from propanol, or to propanol in this case, to propanone.